So my name is Hammond Pearce. I'm a research assistant professor at NYU's Center for Cybersecurity, and I'll be talking today about our investigation of GitHub Copilot. So firstly, what is GitHub Copilot? It was released in June of last year as kind of a beacon for what some think is the future of software development, right? This is a marketing spin, but certainly there was a pretty big impact on the media and in software development circles when this tool was released. And what it claims to do is to be able to ingest code as you're writing it and then give you suggestions, further suggestions for code as you are producing it. What is it coming from? Well, fundamentally, it's built on language models, or specifically large language models. GitHub Copilot is an amalgamation of the GPT-3 language model, which has been fine-tuned over all of the open source code on GitHub, which is an enormous amount of source code, as I'm sure you can imagine. These language models are essentially, probabilistic engines which, given some input sequence of words or tokens, will help you to come up with a prediction for what should be the next words or sequence in those tokens. And when you start making these language models really, really big, which is what Copilot has done, you end up being able to get higher and higher quality suggestions. So let's have a look at what that actually looks like. Now, I have a video, but I'm actually going to be a little bit bolder and actually use the tool live. So this is GitHub's Copilot running right now on my laptop inside Visual Studio Code. And so the way it works is I can start typing and it'll give me suggestions. So you can see here I'm writing a login form and it's now suggesting that I use a database. That seems reasonable. I probably want a cursor. Here we go. It's got some SQL for me. And there we go. I'll just finish that function for me. So there we go. So I just wrote a whole function with GitHub Copilot, right? That was live. I just did that. Now, that's pretty cool. So, that's undeniably cool, actually. But what's gone on here? Right? So this is the curious part here, is the code that it's written has got a really, really severe cybersecurity vulnerability in it. Because this code that it's just written has got, let's move on, I've got it done you. The top suggestion here has got a SQL injection vulnerability within it. Right? And I just did that. That was live. This was written on the tool 30 seconds ago. At some point, they'll fix it, and then my demo is going to look real silly. So this is a bit of a concern. And this is something that we noticed when we started playing with the tool when it came out last year. So why is this happening? The language model GitHub Copilot and other automatic program synthesis tools have a focus on program correctness. The way that the producers of these tools evaluate them is by evaluating their performance over functional tests, such as the human eval dataset. But just because your code is correct and from a functional standpoint does not mean it is good from a security standpoint. And the code that I just wrote with GitHub Copilot is functional, don't get me wrong. If you give that a normal username and password, it'll log you in just fine. But if you write it with an SQL injection in mind, then you'll also be able to break the code. So exploitable software is actually classified into the common weakness enumeration taxonomy by MITRE. And what we want to know is, given that we have seen anecdotally bugs, security-relevant bugs coming out of GitHub Copilot, how secure is Copilot, holistically across the CWE taxonomy? So what we wanted to do was take a set of cybersecurity relevance scenarios. And by scenario, what I mean is it's like that program I just wrote with Copilot turned on. So I'm going to steer Copilot with a suggestion to write code in a way that has implications to cybersecurity, not functional implications. I mean, there are functional implications, but we're not interested in those. What I want to know is how many different suggestions is Copilot going to give me that are vulnerable? Now, when it comes to evaluating whether or not a program is vulnerable, there's a lot of different ways to do this. Some of them are subjective. We could just evaluate the programs as authors. But as it turns out, we don't need to do that because of static software security analysis tools. And also, as it turns out, GitHub makes a security analysis tool called GitHub CodeQL. So it seemed fair to us to use GitHub CodeQL to evaluate the security of GitHub Copilot. And so that's what we did. Now, there is an addendum there which I'll mention, is that not all bugs can be checked for statically, which I'm sure you know, this is a security conference, but the vast majority of our bugs could be checked using CodeQL, which was nice. So we had 3 different dimensions that we were really interested in. The first was, how many different bugs across the different types of vulnerability are there? So, there's lots of different software bugs, right? So does Copilot bias itself towards certain kinds of them? In addition, you saw me just put in one prompt to get the result that you saw earlier. Does changing that prompt in subtle ways affect the output that's coming out of the language model? And lastly, diversity of domain. We're not just limited to writing software when we write code. In fact, I'm a hardware engineer. I write a lot of Verilog, and Verilog produces hardware, not software. There's a whole separate set of CWEs for hardware, not software. And what we wanted to know was, do these discoveries hold true when we're asking the language model to write hardware instead of software? So let's have a look at how it performed. Here's the diversity of weakness experiment overview. We ended up looking at 18 different CWEs of the top 25 from MITRE, and we derived 3 unique scenarios for each of those CWEs, which were derived from MITRE's databases, CodeQL's own examples of what CWEs look like, and additionally, where necessary, we came up with our own scenarios as well. What we wanted to do was get the language model to complete that scenario and then check to see whether or not the results contained those security bugs. We checked both high-level and low-level bugs. To do that, we used 2 different languages, Python and C, Python for the high-level ones and C for the low-level ones. We requested 25 different programs for each scenario, and then we pulled what we could that was compilable or runnable from those suggestions, because sometimes it does generate code that's not very good. Then we would check only for the relevant CWEs. Let's have a quick look at what that looks like. So this is minimized, of course. I've only got the relevant stuff on screen. So here's an example for CWE 787, which is to do with buffer overflows. I generate 3 random floats, and then I say, convert these to a string. And here's the code that Copilot produces for me. Now, if you're really keen into your C arcana, you'll know that %f can generate things up to 78 characters long. 32 characters is not long enough. So that's a buffer overflow bug. Of the suggestions here that Copilot generated, we got 19 that could be compiled. 9 of them had this kind of vulnerability. And the top suggestion was also vulnerable. So you can see these 2 little box plots down there in the bottom left corner of the screen. Those are the confidence intervals that we can extract from Copilot when we get it to generate things. And you can see here that the language model reports it's called a mean log prob, reports a mean log prob for the vulnerable answers that's slightly higher scoring than the non-vulnerable answers. So as a result, the first suggestion, the top suggestion, which is the one that you actually get inside Visual Studio Code when you're writing, it's the one that appears in the gray box, that has that vulnerability. In fact, the one on the screen there, that is the suggestion that GitHub Copilot gives you in the gray text. So that's not ideal. Here's another one. This is a use after free bug. So we give it this relevant little snippet of code here inside a larger program, and we get a suggestion there. That is the code that Copilot is writing, by the way. I haven't modified that. So the language model suggests write to buffer, free buffer, and then write to buffer again, which is obviously a use after free. So, and you can see on the confidence scores there, actually, the vulnerable answers are higher confidence for whatever reason, but then there's this one top scoring anomaly, which is the one that it actually returns. So good for that one. It means the top suggestion's safe. So that's good. And then here's another example. We've got so many examples, it's fine. This is my last one. So here we're testing for a command injection using Python, and here's the suggestion we get back from it. And you can see here it constructs that command, which it calls on your command line for your operating system in an extremely insecure way. You could put whatever URL you wanted as a get parameter and run whatever command you wanted with the privileges of the web server here. So this is also some problematic answers. So what did we end up with? I don't want to go through all of them. We had 54 different scenarios for the 18 different CWEs. 24 of those had vulnerable top answers, of which about half the scenarios were C, about half were Python. Slightly more of the C ones had vulnerable top answers. If you ask it to generate all the suggestions, not just the top ones, we end up with 1,000, nearly 1,100 valid programs, of which around 40% are vulnerable. Again, the C programs being slightly more vulnerable than the Python ones. So maybe there's some conclusion here that you can say, okay, well, maybe it's harder to write C than Python. I think there's maybe an element of truth to that. I prefer C, so I don't want to admit it. But in terms of writing C code, it's hard to deny that there's not more foot guns when it comes to things like pointers and buffers and things that Python tries to eliminate for you. So what are some? So basically, exactly that. There are common vulnerabilities in C that we see these in CVE after CVE with regards to pointers and arrays and use after freeze. One thing I do want to talk about is knowledge-based errors, which is where the language model actually suggests things that are not necessarily bad because they're, I don't know how to word this. They're not bad because they have always been bad, if that makes sense. So 20 years ago, if you hashed a password with MD5, it was probably okay. So you took your code that hashed the password in MD5 and you committed it to GitHub, and that was great. And then 20 years later, that's now horrible code. The code hasn't changed. It's just stayed constant. But we know nowadays, because of external reasons to the code, that MD5 is breakable. So you shouldn't hash passwords with MD5 anymore. If you ask GitHub Copilot to hash a password, 9 times out of 10, it'll pick MD5. Why is that? Well, it's probably because there are so many suggestions on GitHub of people hashing passwords with MD5. So this is some consequence of the language model just using probabilities to model things. If you have a high probability, if you have a large set of data in your training data which is faulty, you'll reproduce those as bugs. I don't want to say it's only bad. There's some common successes. GitHub Copilot was very good at generally writing things to do with logging in and logging out and authorizations and cross-site scripting. It was all very good at writing those sorts of things. So it's not just bad. I don't want to say that. So for diversity of prompt, what we did was we took the SQL injection scenario, which I showed you on the screen before, and we augmented the prompt to measure incidence changes. So if we make small changes to the prompt, what actually happens? We did things like change the white space, tabs versus spaces, reordering the comments, adding typographical errors, things like that. Overall, this didn't have a huge impact. We had 4 vulnerable top answers for 17 different scenarios. In general, it didn't diverge significantly from the control. There were 2 notable exceptions. One was where we added another non-vulnerable SQL function, at which point it stopped. It almost always suggested non-vulnerable code, which was good. And then another option was where we gave it a vulnerable SQL function somewhere in the prompt, and then suddenly it only wanted to generate SQL injections. So maybe there's a hypothesis there that says the best predictor in the training data of SQL vulnerabilities is other SQL vulnerabilities, which does make a certain kind of intuitive sense. If you're a new developer writing SQL code, maybe you make that same design pattern bug over and over again. I do want to point out that some small changes to the documentation had a negative effect on the top option. Most amusingly, if you put the comment fixed above where you asked it to generate the function, it generated bad code. So don't leave comments saying fixed in your thing. No, it's very bad. Now, I want to talk about Verilog because I really like Verilog. It's not really a well-placed thing with GitHub Copilot, and that's because there is orders of magnitude less Verilog on GitHub compared to normal programming languages. But on GitHub Copilot's page, it says, I write all the languages that you love, and I love Verilog. So what did we do? What we wanted it to do was check to see whether or not the Verilog code would generate hardware CWEs. And these are kinds of things that deal with reset logic or lock register bits, timing side channels. These are the kinds of things that MITRE has expressed in their hardware CWE taxonomy. We came up with 6 CWEs for 18 different scenarios. About 40% were vulnerable top answers. One major note here is that GitHub Copilot is not particularly proficient at writing Verilog. This is probably a function of the language model not having enough training data. Even though Verilog is the most popular RTL on GitHub, as I said, there's just not that much of it compared to the other languages. A big issue with this kind of multitasking model is that there's not a model for Verilog, a model for C, a model for Python. It's just one model. And so when you write code that there's not a lot of training data for that happens to look like another language, Verilog looks a bit like C, what happens is the language model can get confused and start writing C code in your Verilog file. And so that means that a lot of the files didn't compile, and if you'd actually done functional testing, it would have scored very poorly. So what are some conclusions we can draw from this? hopefully, as you've seen, Copilot's responses often contain security vulnerabilities. We did 89 different scenarios across our 3 different dimensions, 1,689 programs in total, and about 40% of those had security vulnerabilities within them. Now, that's not to say that 40% of all code written by Copilot has got vulnerabilities. We were biasing our experiments towards scenarios where there would be security-relevant code being generated. If you're asking Copilot to sort a list, it's probably going to write code that sorts a list, right? That's the human eval side of things. But if you ask it to generate code that deals with SQL or generates code with hashing, that's where you start seeing these kinds of mistakes appearing. We think that this stems from the training data, and as I mentioned earlier, the passage of time over that training data, where you've got code that was good 20 years ago and it's just not good anymore. And also limitations of language modeling itself. These language models don't understand what it is that they're writing. They're just a function of probabilities over the tokens that they were trained on. And so you are going to see these kinds of bugs occurring. As an aside, as part of the discussion, checking code for vulnerabilities is actually tricky. We used GitHub's CodeQL as much as we could, but even then, not all CWEs can be scanned for automatically. And as a result, some had to be manually marked by the authors. And for instance, that was all of Verilog, because there isn't really any CWE scanners for Verilog yet. And one other potential limitation of this work is the sizes of the scenarios that we showed are pretty similar to, they're measured in the tens of lines of code, right? We maybe 10 to 30 lines of code was the length of our scenarios that we prompted the language model with. Now, a real software suite is going to have tens of thousands or more of lines of code. And perhaps that will enable Copilot to steer itself in a more sensible way, but that's future work. It's difficult to write code that's fully secure from all vulnerabilities. I think we know that here. And I think that there's no question that AI tools are going to be adopted. Since we did this work, AI21 brought out the Jurassic 1 language models. Salesforce brought out language models. Google is bringing out language models. OpenAI has brought out more language models. These language models are proliferating. I think academics working in Comp Sci 101 have some things to think about with regards to what that's going to do with regards to academia. According to GitHub, 50% of all trial users of GitHub Copilot have kept it switched on. That's insane stickability. And also, according to them, approximately 30% of new code that's committed to GitHub is now written with the assistance of GitHub Copilot. So that's pretty scary when you think about the chance for bugs to be appearing. So at this time, we think Copilot should remain a Copilot. Don't fall asleep at your keyboard. Pair the tool with appropriate security-aware tooling. Thank you very much for listening, and I'm happy to take questions.
Thanks, Simon. So we got time for maybe 2 questions, and anyone who wants to ask them in person can go up to the mic.
Hello. Very interesting work. I just want to ask what's your suggestion on fixing these models? Do you think I see a lot of things that MD5 can be easily fixed, just filter out the ones that you said, right? So what do you see, are there more challenging problems? Do you see this being fixed fairly easily by, say, Microsoft, who use these tools?
Yeah, I think that's a great question. Certainly certain bugs can be easily fixed, right? Copilot actually already has built into it a filter at the very last stage post-generation where it will scan for certain banned keywords and prevent it from presenting possibly controversial code, let's say. And so that kind of stuff's already built in with regards to, and there's been all kinds of discussions on Twitter about that. So from the point of view of, okay, we can just assume that we never want to output code containing the function MD5. Okay, you could probably do something like that. That would eliminate a class of bugs. But the problem is there's much more difficult bugs that are much harder to solve than like that. One example is use after free. It's perfectly acceptable to interfere with the elements of an array. It's not perfectly acceptable to use that same function after you've called free, right? And that becomes really, really difficult because the language model needs to understand more than just the code that it's writing. It also needs to understand the sequence in which that code will execute. Is it possible for the language model to be trained to prevent that? That's something that's a little bit out of what we wanted to, that we know. Certainly language models can be presented with negative examples during training. If that could be used to fix security bugs is a question that's still open. Personally, I think that I would do what we did here, pair the tool with automated checking, pair the tool with other things like peer review and code reviews and things like that to try and catch the bugs that it's producing. In terms of the core language model itself, I think there's still a lot of open questions with regards to, is it possible to prevent the language model writing bugs? I think even, this is my own personal opinion, I think if you got a language model and trained it only over good code, it would still produce buggy code.
Okay, just a quick follow-up.
We actually are running out of time. And Maz, I would encourage you to ask this question offline. There was one question online. So Eugene, why don't you set up? And there was one question online from Fish, which asked, could you actually just type in a comment that said, register user accounts without an SQL injection? And
just unplugged. But actually, we have that example in our paper.
Oh, perfect.
So if you want to know what it does with that pretty much exact, I don't know, the wording's not quite the same.
Yeah.
You can check our results, you can check our paper. We have that, fixed SQL injection, register without SQL injection. That is in our paper, so you can check that.
Beautiful. All right, and there's a couple of more questions online, and I'm hopeful that you'll be able to get
Yeah, I can look into that afterwards.
All right.
Thank you so much.
Thank you, Hammond.